So here we're solving this differential equation. Before we get started, I want to comment on the y greater than 2, x greater than 0 portion. I did not include that in the original problem because I didn't want to confuse you this early on in your studies. And it's almost ignorable information for the most part, but I will make comment. I will address that issue later when we realize as to why I mentioned that earlier. But it doesn't affect the mechanics of the problem, so here we go. Notice we have a differential equation, an equation with differentials. One way to solve differential equations, in fact, one of the only ways you may know at this point, is the separation of variables technique. There are more later in the course, but for now, we've got to separate our x's from our y's. Remember, the dy dx symbol for derivative that you see there, while technically has never been thought of as a division or fraction problem, is actually going to be treated that way for the purposes of solving this differential equation. So I'm going to do some cross multiplying and arrive at this. You may want to hit pause and try to track how I got there. It's basic algebra. But the important thing is I've separated my variables. Why do we separate variables? Because we want to then integrate both sides, thereby eliminating the differentials and having an equation where we can solve for y as a function of x. So what I did here is I didn't show the work. I'll show you the results here. What I did was I did a u substitution for each of these integrals. On the y integral, I let u equal 2y minus 3. On the x integral, I let u equal x plus 4. I did all the math on scratch paper, and this is the end result. You can check that for yourself. And now may be a good time to hit pause if you've forgotten how that works. Moving on. You'll notice I got a plus a on one side and a plus b on the other. Don't we normally write our constant as plus c? Well, we could, but I would be hesitant to put plus c on both sides because that would assume somehow that I knew that the constant of integration was the same number for both of these integrals, and in fact, I don't know that. So I'll put different symbols for my plus c on each side. Now, what I'm going to do next is I'm going to subtract a from both sides, and instead of b minus a, I'm going to write that as c. And you'll quite often see professors, me and others, just writing a plus c on one side to indicate that there were constants on both sides, but we then condense them into a single constant, usually written on the right, not that that matters. Now my goal here is to solve for y as a function of x. My first thought that I had was, I've got this half multiplier there that's kind of annoying. That came from the u substitution, by the way, if you didn't do that yourself. And I thought, well, it sure would be nice if I didn't have fractions, so I decided to multiply both sides of the equation by 2. When I multiplied both sides by 2, the fraction canceled, and I got a 2 times c. But I thought, rather than writing 2 times c, why don't I just call 2c a new constant, give it a new name called d? And that's what I did here. Now, I'm still not in the place where I have y solved for, so I'd like to isolate the y. You'll notice the y is trapped inside of a natural logarithm. The best way to get that y out of a natural logarithm, as you learned in pre-calculus, is to exponentiate both sides. Raise e to both sides of the equation and create a new equation. Now on the left side of the equation, this is an easy simplification because e to the natural log of 2y, sorry about the bell there, e to the natural log of 2y minus 3, or e to the natural log of anything, is itself. Now, at this point, I should mention that the reason I stated that y had to be greater than 2, the original problem for this to be valid, is because if y were anything under 1.5, the left side of this equation would be negative, and we get into some complicating factors there that I just didn't want to address at this early stage. So, putting that aside, the exponential cancels out on the left side of the equation. But on the right side of the equation, the e and the natural log don't directly cancel there because there's too much other algebra in the way. But there is some algebra I can do to that side to get the cancellation that I ultimately want. The first thing I'm going to do is use the sum rule for exponents, which says I can write this up as shown. And remember that the e and the natural log still don't cancel because I have a multiplier of 2 there. But what I can do is I can rewrite that exponential function this way using the basic rules of exponents. And now I have reworked this thing in a way that the e to the natural log of a number is always itself. I arbitrarily had originally chosen x to be greater than 0 just to ensure that x plus 4 is positive and not have to deal with the negative complications that would have arisen here. But the important thing is I've done some algebra and I've eliminated the natural logs completely. Now, in order to solve for y, which is my ultimate goal, I'm going to simply add 3 to both sides and then divide both sides by 2. And now I have a generic solution for this differential equation. It's worth pointing out that you may have gotten a different answer and also be correct because there's so many different ways to lump the constants together here that you may have gone a different path and still been right. And that concludes this problem.